Hi everybody, this is our presentation and demonstration of our magnetic levitator. Our group is made up of Halal Bari, Austin Bordoon, Morgan Butler, Michael Dalton, Ahmed Fali, Jeff Simpson, and Chris Turner. So our team was made up of 5 mechanical engineers and 2 computer systems engineers, making up 7 people in total. The purpose of our project was to use the principles we learned in class to build a magnetic levitator that could levitate an object using proportional and derivative feedback control system.
To begin the theory behind our magnetic levitator, we first looked at Gilbert's theory, which puts the force proportional to the current squared divided by the distance squared. And on the screen you can see Gilbert's full theory, which also incorporates the number of coils, the permeability of the material, and the distance between the object and sensor and the area of the solenoid head. From our calculations, we found the force of our magnet to be 1.1 newtons strong. In order for us to levitate the object, the magnet must be able to turn off and on very quickly, and this is done through our MOSFET on our circuit board. The infrared sensor reads the amount of infrared light it sees and sends it back to the controller. The controller then reads the sensor and controls the current given to the magnet. The system itself needs to have a stable feedback system in order to function properly. If not, the magnetic levitator will not work and the object will fall or stick to the magnet itself. To get the stability of the system, the poles of the transfer function must be stable. And what we learned in class, this means that the poles must be to the left of the imaginary axis on the S-plane. And so on the bottom right, you see the unstable block diagram, and on the bottom left, we see the unstable transfer function. For the purposes of finding the poles of the transfer function, we set the disturbance equal to 0 because it is an unknown force at this time. On the previous slide, we saw that the poles of the transfer function were unstable because there was no S term in the bottom of the transfer function. So in order to make it a stable transfer function, we had to add a PD controller, and this gives us the S term that we need in the bottom of the transfer function. This also allows us to choose the location of the poles. And so below you see the block diagram of the system itself, and below that we have the transfer function after the controller is added. We can see that the S term is there, and we are now able to control Kp and Kd to create a stable system.
We had to build a sturdy frame to support the electromagnet and a housing for the controller. We decided to make both from extruded aluminum, plexiglass, as well as machine screws and T-nuts. We had 3D printed adjustable brackets to be able to move our infrared light emitter and our infrared light sensor to be able to change heights. We also included an Arduino Uno as our controller, a MOSFET, a 10K resistor, jumper wires to connect it all, and a pulse width modulator.
For our project, we decided to use an old laptop battery supply that supplies 19.5 volts and 3.3 amps to our magnetic levitator. We built our electromagnet on a 3D printed spool, which is shown here in blue, and it's wrapped with 24 gauge copper wire, which is in red. So like I said earlier, our magnetic levitator was built using the 3D printed spool, and it is made out of 1,000 turns of the red copper wire. The solenoid is attached to the levitator itself by 2 bolts through the 3D printed plastic, and the middle core of our solenoid is a 3-inch long steel bolt. And we needed to be careful that we didn't leave our magnet on too long, or else we would run the risk of the heat generated from the magnet melting our coil itself.
The circuit diagram is pictured here, and its connections are as follows. The IR emitter is connected to pin 13 of the Arduino through a 100 ohm resistor. The IR sensor is connected to pin A0 of the Arduino through a 100 ohm resistor, which is connected to 5 volts. The leftmost gate of the MOSFET is connected to pin 11, which allows the Arduino to control the current feeding through the solenoid. The positive terminal of the power supply is connected to the positive lead of the solenoid through a connection to the diode. The middle gate of the MOSFET connects the other side of the diode to the negative lead of the solenoid. The placement of the diode is important because it only allows the current to flow in one direction. The negative terminal of the power supply is then connected to the rightmost pin of the MOSFET.
The object we chose to levitate was a screw with 8 nuts. As you can see in the picture, the majority of the nuts are located at the bottom of the screw to give the object a greater moment of inertia to help stabilize it while it's being levitated. We went through a trial and error process to find the optimum weight as well as stable values for Kp and Kd. The way we attached our sensor allowed us to vary the distance the sensor would be from the magnet. During our trial and error process, we found a sweet spot when the sensor was 1 inch from the magnet. While we were testing the ability of our levitator, we were powering it using a power supply in the lab, but we wanted to power it using an old laptop charger. However, when we first tested the system using the laptop charger, the system was unstable due to the fact that the charger wasn't meant to hold a steady voltage, whereas that's the purpose of a power supply in the lab. As we were experimenting with objects we could levitate, we noticed it worked best when the object had a flat top. This prevented any unwanted spinning that could cause the system to become unstable. This instability started with small oscillations that grew until the object fell from the sensor path.